early days of flying, getting out of a damaged airplane safely was not too much of a problem. That is, if the parachute opened. Today, the problem of getting the pilot safely out of a supersonic interceptor at extreme altitudes and high Mach numbers is a growing challenge. Present ejection systems are satisfactory for subsonic ejection. However, the need and urgency for developing an ejection system that will function at subsonic, transonic, and supersonic speeds at minimum and maximum altitudes is vital. In view of this, the Industry Crew Escape Systems Committee was formed, representing most of the aircraft and airframe manufacturers producing airplanes for the U.S. Air Force. The task, to develop a supersonic seat ejection system compatible with existing airframe configurations and in harmony with advanced aircraft planning. The task was assigned by Air Research and Development Command and the Air Materiel Command, working jointly in the supersonic seat ejection program. Convair, a division of General Dynamics, was assigned the responsibility for the upward ejection seat for Century Series aircraft and the integration of components manufactured by subcontractors. There were 2 seats under consideration. They were for an A and B configuration, so a dual program was begun. The outstanding feature of the A seat was the skip flow generator, which deflects the airflow, reducing wind blast. The distinguishing feature of this B seat was the pilot's position at time of ejection. This seat is referred to as the bobsled. The likeness is readily discernible. The pilot is ejected at a 90-degree launch attitude. 1/10 scale models of the A and B seats were checked in wind tunnel tests to establish trajectory, pitch, yaw, and roll. Wind tunnel tests on the B seat with a 45-degree fin indicated that its stability factor was superior to the A seat because of its general flight characteristics. At the suggestion of the Lockheed Engineering Department, it was decided to run a series of slingshot tests on both configurations. Results of extensive slingshot tests on the A model verified the wind tunnel tests indicating instability. Therefore, with the sanction of the ICESC committee, Convair decided to concentrate its efforts on the development of the B seat. During the same period, Northrop Aircraft Company, a member of the ICESC committee, was completing the fabrication of the wind blast rocket sled for Convair. The B seat was to be tested on this sled at the experimental track branch at Edwards Flight Test Center. This life-size model of the seat, subcontracted to the Stanley Aviation Company of Denver, Colorado, was attached to the sled to make sure all fittings were compatible. A short time later, wind blast runs were set up at the Air Force Flight Test Center. These runs would indicate the wind blast forces on the seat and pilot. Results showed that present Air Force garb stayed intact except for superficial parting of the seams and partial opening of zippers. To attain higher Mach speeds in subsequent testing, a pusher sled is employed to give additional thrust. In all, there were 5 runs conducted at speeds of Mach 0.95 to Mach 1.30. Both low and high altitude flight gear was examined for wind blast results. The pilot and his personal equipment was found to be in near pre-run condition. Concurrently with the wind blast program at Edwards, there were 5 seat ejection runs to be conducted on the ARDC Supersonic Missile and Rocket Track at Hurricane Mesa, Utah. This promontory was selected for its unusual physical shape, a high elongated rock formation that would easily accommodate a long sled run of 12,000 feet, with a sheer drop from the mesa edge to the floor of the desert 1,500 feet below. The straight drop allows better observation to study seat trajectory characteristics. The seat was attached to the fixed platform with breakaway bolts, which would release the seat at the predetermined time. The breakaway bolts and rocket motor are products of the Telco Engineering Company of Hamden, Connecticut. The two antennae on the forward end of the seat receive a radio impulse which deploys the parachute on signal. The sled attained an equivalent speed of Mach 0.95 at sea level. Flight time of the seat was approximately 12 seconds. 3 objectives were accomplished on this run. 1, the full-scale seat simulated ejection performance as planned. 2, the validity of the slingshot tests were verified by the flight attitude of the seat. And 3, the test confirmed the results of the previous wind blast tests on the pilot and personal equipment. There was no appreciable damage to the seat or pilot, and the flight gear and helmet remained in pre-run condition. This seat configuration had good yaw and pitch stability, but did have excessive roll. However, the roll was within human tolerance. Because of the roll encountered with the B seat on the first run, additional slingshot tests were conducted on scale model seats with the addition of a new device. This consisted of telescopic booms extending from the top of the seat. These scale models were submitted to another series of slingshot tests. The new telescopic booms indicated exceptional stability. With evidence that the roll had been substantially reduced, additional runs were scheduled at Hurricane Mesa with a life-size seat equipped with the telescopic booms. The purpose of these runs was to expediently establish the flight characteristics of the seat. Therefore, it was fired from a fixed platform, simulating the launch position attained after the seat has been raised and rotated out of the cockpit. Later firings included the sequencing of the seat from inside the cockpit to launch position. The rotating equipment was still undergoing refinements at the time of these tests. On this test, the seat flew perfectly, with no pitch, no yaw, and with a negligible roll of only 270 degrees. As the seat left the sled, a delayed powder train was set off. After 10 seconds of flight, a drogue gun in the parachute pack was initiated. During the last test at Hurricane Mesa, the sled attained an equivalent speed of Mach 1.15 at sea level. On this run, the 2 forward breakaway bolts failed. The wind caught the seat and tilted it up, causing the aft bolts to fail. This took place before the trackside mechanism for firing the rocket and the time delay device for releasing the parachute was set off. The seat and dummy rose to a height of 375 feet and cleared the ICESC composite fin. This trajectory was due entirely to aerodynamic lift characteristics of the seat. This means that in this speed range, a safe ejection is possible even if there is a rocket failure, and indicates a good fail-safe feature for emergency situations. As a result of these runs, the boom seat proved to have excellent flight characteristics, and the test program was considered very satisfactory to this point. Having established the seat trajectory at Hurricane Mesa, the testing program was transferred to Edwards Air Force Base. This move made Convair and Bender facilities more accessible for continuing simulated cockpit ejections from Century Series aircraft. On July 2nd, 1958, at the Air Force Flight Test Center at Edwards, a supersonic sled test run was conducted. The sled attained an equivalent speed of Mach 1.10 at sea level. The seat rotated from the normal operating attitude to the launch position and was rocketed away to an altitude of over 700 feet. During rotation and rocketing, the loads recorded were well below human tolerance, and flight characteristics showed a substantial clearance of the composite fin of the Century Series aircraft. The results of the July 2nd run confirmed many previously assumed hypotheses. The task of detailed design, development, and hardware fabrication still remains to be accomplished with vendors of the individual components. However, a basic supersonic seat configuration which has the capabilities of successfully ejecting crew members from any existing Century Series aircraft, regardless of the speed or altitude, is now a reality.